Okay, 11.6. So we're going to talk about additional temperature related material properties. Basically, we're going to talk about thermal expansion and specific heat.
That's symbol alpha.
Thermal expansion and specific heat. Okay, thermal expansion. So when you heat something up, you heat a metal up, okay, it's going to expand. Okay, it's going to expand. Just as though when you have put a metal in a cold place, it's going to shrink. Okay, just so if you look at the alpha on the example on the equation 11.27, bottom of page 382, you have alpha L, the linear thermal expansion is going to be equal to delta L over delta T with an L here. So basically this is the relative expansion. Can you see that, right? Because it depends on how much it expands, depends on how much there is, right? Right, if I have a 100 centimeter long rod versus a 200 centimeter long rod, if you heat it up, the 200 centimeter log is going to expand twice as much. Makes sense, right? Okay, so this is the relative expansion right there, relative, right? Relative to the L, okay? This is going to be the delta T, right? Okay, so there you go. So that's what it looks like. If you actually can change this and say delta L is equal to alpha L delta T, and you can calculate directly what the delta L is going to be for that amount of heat. So the more heat that you put, the greater the temperature difference, the greater it's going to be, which makes sense. Okay, all right. So if you look at page 383, there are some thermal expansions there, thermal coefficients there. So which ones are large, which ones are small? Okay, first of all, they're obviously very small, right? 10 to the negative 6th here, right? 10 to the negative 6th, okay, some of them have 10. What's that, bronze? See that? Bronze is 10 times 10 to the negative 6. Okay. And then what else is there? What's small?
Masonry? No.
Masonry? Yeah, masonry's going, well, yeah. 2.7, wood. Right? Obviously wood's not gonna, wood's probably gonna, huh? Glass, okay, yeah. Yeah. So, just realize that it seems like this, things like this. If you go flip the page, they give you a different one, and what does that say? So this is the thermal expansion in volume, not length, right? So again, you're going to have a delta V over V situation, right? You're going to have a delta T here. Okay. And that's the same thing on page 384. It tells that, and actually it gives you the relationship between these two, right? The volume is 3 times the linear, which makes sense, right? Because volume is linear to the third, right? So you have 3 different ones there. Okay. Okay, let's look at specific heat. Okay. Specific heat provides a quantitative way to show how much thermal energy is required to raise the temperature of a 1 kilogram mass of material by 1 degree Celsius. Okay, so the amount of energy that it takes to raise a 1 kilogram mass by 1 degree Celsius. Okay, that is what the definition of a specific heat is. Okay, if you look there, the thermal energy says that the thermal energy is equal to mc, that's a C delta T, right? Delta T. Okay, so M would be the mass there, right? M would be the mass. This would be this specific heat. This is the energy that's required, and this is the delta T. Okay, so if you put in 1 kilogram here, right, 1 degree Celsius here, you can see that C is going to be equal to energy, right? Okay, right? 1 and 1 here, right? 1 and 1 here, right? Okay, all right. So that's basically it's really a definition. Okay, all right. So some materials are going to heat faster or quicker than others, or with less delta T there. Okay, so if you go to table 11.13, you have different values there. Okay, so the larger the specific heat means what? It takes more energy, right? The larger the specific heat, the larger the energy is required to raise 1 kilogram, 1 degree Celsius, right? So water, huge specific heat, okay? Air is about 1,000. You have things like lead, which heat up, you know, just like that, really quick, okay? All right? So there you go. So that is what specific heat is, really, okay? And that's it. That's it. Okay, pretty quick, nice and short.